Representations of numbers. In this chapter, we're basically just converting between decimal, binary, hexadecimal, and octal. The book has a few definitions, such as this definition for decimal numbers, which breaks down the number system that we know into more mathematical terms. So given a positive integer x, the decimal representation for x is a string consisting of digits from, well, between 0 and 9. That looks like d sub n minus 1, such and such, until d sub 2, d sub 1, d sub 0. So that's basically d sub 0 is the ones place, d sub 1 is the tens place, d sub 2 is the hundreds place, and we can see that by thinking about 10 to some power. So we have this summation down below. We have our digit times 10 to some power, and that gives us our ones place or hundreds place or whichever. So if we break down this sum, we'll see that 10 to the 0th is equal to 1, so the ones place is some digit from that set, 0 through 9, times 1. Then the tens place is 10 to the 1st, so again we take a number from the set, 0 through 9, and multiply it by 10, and that's our tens place, and so on and so forth. And we can basically do the same sort of thing for binary numbers, but instead of 10 to some power, it's 2 to some power. So the definition of a binary representation of a positive integer x is a string consisting of the digits 0 and 1 that look like, again, a string of numbers from b sub n to b sub 0. So here, instead of having ones place, tens place, 100s place, we have 1, 2, 4, and 8. So powers of 2 are our positions in the string. So here we have 1, 0, 1, 1. In the ones place, we have 1 times 1, so that counts as 1. In the twos place, we have 1 times 2, so that's 2. 2 plus 1 is 3, so that's 3 at the moment. 4's place is 0, not adding anything there. 8's place is 1, so that means 8 times 1 is 8. 8 plus 3 is 11. So the numbers that we're covering are hexadecimal, so those go from 0 to 9, and once we get to 10, or basically a 2-digit number, we are going to replace those with A, B, C, D, E, and F. So then we have octal, which is base 8, so it goes from 0 to 7. And these are the main number systems that we're concerned with. So when we're working with computers, we see hexadecimal quite a bit, such as memory addresses for our variables. We can also make a binary number easier to read by converting it to hexadecimal, and converting that is pretty easy. So to convert between a decimal number and base 2, the book gives us this algorithm. So first we have the input of some number n, and while n is greater than 0, we'll do the following. We divide n by 2, because it's base 2. We get a quotient and a remainder, and then we write r as the next digit in the string, but we go from right to left. We replace the value of n with q, and then we repeat. You can even implement it in a program, so I've gone ahead and done that in C++. So here's a simple program that will convert from decimal to binary. I just need to build and run it. And now we can enter some decimal number, so let's try just 1. In binary, that's 1. Let's try 2. That's 1, 0. 3, that's 1, 1. 4, 100. Well, 1, 0, 0. 5, and so on. So we can check a bunch of different numbers here. So the letter A in ASCII, just so you know, is 65, capital A. So you'd see something like this. And then the letter Z is 90. So if you have a binary number of usually 8 digits with a leading 0 and a 1 in the 64's place and a bunch of other stuff, you can usually tell it's just some text that's been converted to binary, and you can check it out this way. So 65 is A, 90 is Z, and you can kind of just convert it from there. Okay, so let's actually work out some conversions between these numbers. Alright, so I'm going to show you 2 different ways to convert from decimal to binary. We'll go with the book's algorithm first, so let's convert 6, because 6 is going to be 110, which is, this is the 1, 2, and 4 place, and you just add these up, 4 and 2. So let's check out the algorithm. So first, n is 6. So we'll do 6 divided by 2. That goes in 3 times, remainder is 0. So q is 3, r is 0. So by here, we write the remainder as the rightmost part of the string. And now n is q. So next time we're doing n is equal to 3. 3 divided by 2, that goes in 1 time, and that's going to be a remainder of 1. So q is 1, r is 1, so then we'll put r as the next digit, and this is our new n. So n is equal to 1. 2 divided by 1, well, that doesn't really go in at all, so we end up with a remainder of 1. So q is 0, r is 1, and we'll put 1 as the next digit. So now n is equal to 0, we're done with the loop, and this is our string for 6. So I'll show you the method that I usually use when converting from decimal to binary. So I have 66 here. I'm going to basically write out my places until I get to something larger than 66. So we have 8, and we have 16, 32, 64, and 128. And so basically I just go through, I keep subtracting it by each of these numbers, and I put a 1 if I'm able to subtract. So for example, I cannot subtract 66 by 128 and get a positive number. So I'm going to put a 0 here. Basically, I can't. But I can subtract 66 from 64. So I'll put 1 here. And they'll say 66 minus 64 is equal to 2. So now 2 is our new number. I can't subtract 2 from 32, 16, 4, or 8, 4. But I can subtract it from the 2's place, so 1. And then now 2 minus 2 is 0, and I can't subtract it from 1 and get a positive number, so this is our 66. So this might have been better with something a little bit larger. Let's try the letter Z. So this is Z, this is B, capital B. So again, 128 is going to be 0. We have 64, 32, 16, 8, 4, 2, and 1. So 90 minus 64, maybe I'm not very good at doing math in my head, but that's okay, we got calculators, right? So 90 minus 64 is 26. So I can subtract this, that's fine, I'll put a 1 there. I can't subtract 26 from 32 and get a positive number, so I'll put a 0 there. I can subtract it from 16, and that will give us 10. So I'll put 1 here, and we have 10. So I can subtract 10 from 8, or I can subtract 8 from 10 rather. 10 minus 8 is 2. So now I'm not going to subtract this part. I will subtract here, and I won't subtract here. So that works out to this digit, and again, we can run this program just to double check it. So we'll translate the number 90. Now this one doesn't add the leading zeros. Usually in binary, it's nice to have groups of 4, because a byte is 8, and I believe a nibble is 4. So 0, 1, 0, 1, 1, 0, 1, and then the leading 0. So that's how I usually convert between decimal and binary, but you can also use that other algorithm. So on the review sheet, I also have some examples of converting from other things. So really, I just kind of prefer to do the same sort of thing. Convert 35 from decimal to base 5, and so we'd have 5 to the 0 is 1, 5 to the first is 5, 5 to the second is 25, and 5 to the third is 125. So the same sort of way as I convert to binary, I just go up until I hit something larger than my number, and then we start subtracting. So nothing here. Now this is going to be a little bit different. We can subtract 35 from 25 one time, so 35 minus 25 would be 10. So here, this would be just one time. We're only subtracting it one time. Now here, I can subtract 10 by 5, and that equals 5. I can actually subtract this twice and get my 0. So since I'm subtracting it twice at this position, I'm putting a 2. Remember, with base 5, or with whatever bases, we have basically 0 until that base, whatever that number is, as digits we can use. So I've subtracted this twice. Now I have a 0, so I won't subtract here. And we can see this here. You can also double check it just by going the reverse way. So remember, this would be 0 plus 2 times 5. So 2 times 5 plus 1 times 25. And then a 0. And so 25 plus 10 is equal to 35, and that's how you would check. So here we have convert 35, which is octal, to a decimal number. So in this case, I also did 8 to the 0 is 1, 8 to the first is 8, 8 to the second is 64, and I basically kind of did the opposite way around. Instead of subtracting this from everything, because we're going the opposite direction, we're converting to decimal, I wrote this in each of the places. So 0, 3, and 5. This is the octal system. Rather than subtracting each one, I am putting everything in its place so that we can properly get the decimal number. So remember, our decimal number is going to be our ones place times however many times we're going to do that, plus our eights place and however many times we're going to do that, and then 0 of 64, so 64 times 0. So here we'd have 5 plus 24, and that should be 29. So that's our decimal number, 29 base 10. And similarly, if we have a binary number, we can easily convert that the same way. We just put these in the proper places and then think about, okay, this is 8 plus 2. That's just 10. Now for converting hex to binary, it's a little bit different. Let's say we have D, A, and D in hex. So what I would do is convert each of these to their binary equivalent. So, okay, maybe we should write out a graph for this really quick. In hexadecimal, we have these digits. We have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then once we get to 10, we start using letters. So A, B, C, D, E, F. So maybe it would be helpful to make up a little table. In binary, this is 0. In binary, this is 1. This is 1, 0, 1, 1. This would be 1, 0, 0. 4's place, 1, 0, 1. 1, 1, 0, and so on. So 4 plus 2 plus 1. So it'll just keep going like this. 1, 0, 0, 1. So 10 is 8 plus 2. Let me just write this as reference. 11, 12, 13, 14, 15. So B, 11. So we have 8 plus 2 plus 1. 8 and 4 would be 12. 12 and then plus 1. 14 and 15. Okay, so we have this chart. And now we're going to convert D from hexadecimal to binary. So let's group these as these each 4 digits. So D in binary is 1101, and then in A that would be 1010, and then for D again 1101. Okay. And really that's all you have to do to convert from hex to binary. It's just kind of a matter of knowing what each of the letters stand for, and then since it's basically, you have base 2 and you have base 16, this is 2 to the 4th? Yeah, I think so. So you can kind of just make a direct translation like that.